In example 2, convergence of the p-series. For what values of p is the series 1 over np to the p power as n is equal to 1 to infinity convergent? Now, let's take a look at these scenarios. In step 1, if p is less than 0, then the limit as n approaches infinity of 1 over n to the p power is equal to infinity. Now, if p is equal to 0, then a limit as n approaches infinity of 1 over n to the p is going to equal 1. So in either case, the limit as n approaches infinity of 1 over n to the p is going to equal 0. So the given series is divergent by the test for divergence. Now, if p is greater than 0, then the function f of x is equal to 1 over x to the p is continuous, and it's decreasing on the interval from 1 to infinity. So in step 3, we're going to take the integral as it goes from 1 to infinity of 1 over x to the p dx. It converges if p is greater than 1 and diverges if p is less than or equal to 1. So in step 4, we can say that it follows from the integral test that the series of 1 over n to the p converges if p is greater than 1, and it diverges if p is in between 0 and 1, including the value of 1. Now for p is equal to 1, this series is the harmonic series as we discussed in example 7 back in section 8.2. Now, in order to use the integral test, we need to be able to evaluate 1 to infinity of that function dx, and therefore we have to be able to find an antiderivative of that function. Frequently, this is difficult or impossible, so we need other tests for convergence too.